Hi everyone! We've opened the topic of multivariate analysis MVA in the previous video. There was a reminder that the likelihood ratio method provided, in principle, the best possible discrimination between signal and background events. However, populating a histogram in 5, 8, 10 dimensions or so is impossible with Monte Carlo. And Monte Carlo is the only possibility we have in particle physics most often. In the end, we concluded that it was necessary to find a replacement or an approximation of the likelihood ratio method. This video will introduce some simple but useful methods: orthogonal cuts, projective likelihood ratio, and Fischer discriminant. In the next videos, you can look forward to more sophisticated methods, boosted decision trees, and neural networks. Let's start with the simplest MVA method, with the orthogonal cuts. I'm not even sure whether we should call it MVA method, but okay, it satisfies the loose definition of being based on several variables. The method in one sentence: you identify variables that have some discrimination power, and you apply a cut on each of them. Clearly, you select a line segment in 1D, a rectangle in 2D, a cuboid in 3D, and a hypercuboid in general. The optimization of cuts can be done, for example, with the Monte Carlo events by maximizing the expected significance, or just S over square root of B. You can do it in root with the TMVA toolkit. By the way, TMVA will be cited throughout this and the following videos quite a bit, because it provides implementation of all methods discussed in this course, and it is a part of root that is so well known to all particle physicists. However, you don't have to stick to root. The open source market is full. Go ahead and Google, and you will find great frameworks. The next method to discuss is the projective likelihood ratio. It is an approximation of the likelihood ratio method, and it reproduces it in situations when there are no correlations between the discriminating variables. Simply, you approximate the full n-dimensional PDF by a product of 1D PDFs. Each PDF corresponds to the shape of one discriminating variable. This way, you build the approximate PDF for the signal, then for the background, then you calculate their ratio, and you place the critical region to where this quantity is the highest. Mathematically written, lambda of x vector is approximately equal to the product over j going from 1 to n, f sub j of x sub j given the signal hypothesis, over product of j going from 1 to n, f sub j of x sub j given the background hypothesis, and this is required to be higher than a constant c sub alpha. Obviously, the PDFs for the individual variables, the 1D shapes, are estimated with 1D histograms filled with Monte Carlo events. The gain is obvious. Instead of filling a n-dimensional histogram, you just fill n one-dimensional histograms, each of them with the full set of Monte Carlo events. However, the neglect of correlations might lead to a low performance. You can imagine that an approximation of a very narrow inclined ellipse by a circle might not be the best thing. The last method to be discussed today is the Fischer discriminant. The basic idea is simple. It replaces the full n-dimensional PDF by its projection to one very special line in the ND space. The tough question might be how to find the line. Fortunately, there is an analytical answer to this question. However, don't have overly high expectations. The method doesn't necessarily yield optimal results. Anyway, let's find the analytical solution now. So we assume our test statistic is given by the projection of the full PDF on the special line. We can write it like this. T of x vector is equal to a0 vector plus a vector transposed times x vector. Here, a vector stands for a direction in the ND space, and a sub 0 vector is an offset from the point 0. With the Monte Carlo simulation, mean and covariance of the discriminating variables can be estimated like this. Expectation value of x sub j is definitorily equal to mu sub j, and this is equal to the integral over dx vector x sub j f of x vector, and this is approximately equal to the mean value of x sub j estimated from Monte Carlo events. Variance of x sub j times x sub k, definitorily equal to v sub jk, is equal to the integral over dx vector of x sub j minus mu sub j, all this times x sub k minus mu sub k, and all this times f of x vector. And this is approximately equal to the mean value of the following quantity: x sub j minus mu sub j times x sub k minus mu sub k, and the mean is estimated from Monte Carlo events. These can be used to calculate the mean and the variance of the test statistic. Expectation value of t of x vector, definitorily equal to tau, is equal to a sub 0 vector plus a vector transposed times mu vector. Variance of t, definitorily equal to sigma squared, is equal to a vector transposed v a vector. Of course, the mean and the variance will be different for signal and background events. So we have tau of signal, tau for background, sigma for signal squared, and sigma of background squared. Now we have all necessary components to find the values of a vector that yield the best signal to background separation. We assume that the best separation is obtained by values maximizing the following quantity. J of a vector is equal to tau signal minus tau background, all this squared, over sigma signal squared plus sigma background squared. In fact, we are maximizing the distance between mean values of the test statistic distributions for signal and background. This is definitely desirable. At the same time, we require the distributions to overlap as little as possible. And we do it by minimizing the sum of variances. We are maximizing a quantity that has the sum of variances in the denominator. Of course, the distance of mean values and the width of the distributions can be concurrent effects. Therefore, we have to take them into account simultaneously. J does exactly this. You could argue that maximization of the quantity J doesn't necessarily yield the best possible vector A vector, but it's clear that the result we get with J will be one of the best options. The nice thing about J is that we can express it with simple quantities estimated from Monte Carlo events. J of a vector is equal to sum over j and k, a sub j, a sub k, times mu signal minus mu background sub j times mu signal minus mu background sub k. And all this over sum over j and k, a sub j, a sub k, v signal plus v background sub jk. Let's find the maximum of j by requiring its gradient to be 0. The condition yields a vector max is proportional to the inverse of the sum of covariance matrices v signal plus v background times mu signal vector plus mu background vector. Quite an elegant result, isn't it? Note that the solution vector A vector max can be scaled by an arbitrary factor without any change of the separation power. Also, the separation power of the test statistic doesn't depend on the shift A0 vector. As mentioned already, the excellent feature of the Fischer discriminant is that there is the analytical solution and no training is needed. On the other hand, its discrimination power is generally not optimal.